So although I am in the supermassive black hole section and I love them dearly, I am going to only acknowledge them somewhat glancingly as the host for an AGN accretion disk. And I'm going to tell you about all of the physics that we have to care about in AGN accretion disks, which is a lot longer than maybe the canonical list. So yes, sure enough, first thing on the roadmap is there are things in AGN disks, and they are can be treated in some ways similar to protoplanets in protoplanetary disks. So all the stellar people, guess what? The bridge that you've been looking for, right? Here we go. It may be somewhat Dr. Seuss-like by the end, but so we have to pay attention to migration, and we can already gain some insights because the protoplanetary people have been thinking about this for a long time. So I'll talk about that. I'll talk about stellar mass black holes and gravitational waves, because stellar mass black holes and binaries make gravitational waves that we can detect today, which is very exciting. I will also hopefully get a chance to talk about stars and some things that I think maybe I'll point to for discussion sessions tomorrow. So just to point out, the mass ratios in protoplanetary disks for Jupiter or the Earth to a one solar mass star are similar to what you would have for a mass ratio if you had a sort of largish intermediate mass black hole or a very small SMBH, depending on your central mass SMBH. And Jupiter is a gap opener, whereas stars and stellar mass black holes are down around Earth type mass ratios. And of course, some people might argue, well, star formation in AGN is quite uncertain, and I would 100% agree with that. But it doesn't matter, because we definitely know that nuclear star clusters exist. And so in detail, I will remind everybody what our nearest galactic nucleus looks like. And we know that there is a 4 million solar mass black hole in the center there, and we know that there are these stars that are orbiting around it. At the distance that this is, that scale bar up at the top, 0.1 arc seconds, is 10 to the 4 Schwarzschild radii. So if you were to drop an AGN disk on our own galactic nucleus, there would for sure be stars with orbits that intersect that disk. We also have reason to believe, various reasons. One, those are B stars, right? There were probably O stars there. If they're not there anymore, then we know what they turned into. But there should be on the order of 10 to the 4 stellar mass black holes in the central roughly cubic parsec. And we also know that nuclear star clusters are extremely common, especially around lower mass supermassive black holes. Now, I will point out, as this protoplanetary people will be delighted to remind us, that n equals 1 is always a cautionary tale. This is a fantastically detailed image, and we understand quite a bit about the individual objects that are orbiting around our own galactic nucleus, but we only have this one really great close-up example, and so we can always take that with a grain of salt. However, I think it is very reasonable to suppose that there are stellar mass black holes that live in AGN disks. There should also be stars that live in those disks. And so we can start to think about what some of the consequences might be for both those objects and for the disk itself. And together with collaborators, pointed out about a decade ago that if you have stellar mass black holes in these disks, there are a lot of ways that they might be able to form binaries, which would merge, which would then be detectable via gravitational waves in LIGO. So since then, of course, nothing interesting has happened. I'll come back to that. But the first thing that we can do is just remind ourselves we can borrow the physics from protoplanetary disk modelers, at least to 0th order, and think about what the migration torques might be on stellar mass black holes or stars in similar disks. Since we're under the sort of critical mass ratio of about 10 to the minus 4, we have non-gap opening or type 1 migration. This is broadly speaking typically inwards. There's an asterisk there. The direction does depend on the surface density gradient, and to a lesser extent, there's a secondary effect from the temperature gradient. So you can't just sit down and write out analytically immediately, oh, that disk has one, that one doesn't. But it is the case that when you have a sharp change in the surface density gradient, you will have a change in the migration rate. And we do think that AGN disks have reasons to have significant changes in their surface density gradients. For example, if you go from a gas pressure dominated to radiation pressure dominated regime, whether or not that gets you an outright reversal of the direction or just a slowing depends on the details of what you think is going on in the disk. And just to give folks, especially the students, some intuition, right? These are fundamentally gravitational forces. So as you're changing the surface density gradient or you're changing the mass in one of those spiral arms, that's what's pulling your object around, right? It's fundamentally gravitational. But the reason that feedback matters is because if you're changing the distribution of gas around your object, then you're changing the mass nearby, and gravity, 1/r². It can really change qualitatively the kinds of answers that you get. Since we have black holes, they're sitting in a gas disk, we can reasonably expect that they might be accreting, and so feedback is probably something that we need to do kind of well. However, it is worth noting that we should pay attention to what the protoplanetary people are doing, because they get better resolution on the objects of interest, right? Their objects are much smaller than AGN disks, but they're also much closer, and the closer wins. So they have better resolution on the relevant size scales, and the protoplanetary disks also conveniently leave droppings around, which are also very observable. And so we can infer things about the processes that are going on in disks for protoplanets, and hopefully not have to reinvent all the wheels. So as a protoplanetary people have known for a long time, and as I mentioned, migration can go both directions. So this is work by Gillian Bellovery, who demonstrated in a couple of different models for AGN disks. This is a Circo and Goodman 2003 disk, that there exist migration traps. In the Circo and Goodman disk, they're pretty robust. However, there is a secondary effect from the temperature gradient. So if you do something like change the opacities, you can change that temperature gradient. And for example, Dittman and Miller showed that in a Thomson, Quater, and Murray disk, you can make that migration trap go away. It is not clear what the right opacities are, so this is perhaps a little bit discouraging. But as I said, to some extent, there's always going to be some kind of migration slowdown. And so in that context, you get to have objects that are encountering each other at a low relative velocity and on relatively short timescales compared to the expected lifetime of a disk. And so when they meet, they are pretty likely to form a binary. How long does that binary survive is a little bit unclear, and I think we're going to hear some more about this. I was doing my best to keep my slides updated in light of all of the various archive drops in the last couple of days, which was somewhat challenging. But I think Donglai will hopefully talk about this. The question is, you form a binary, but does it actually close the distance? And so now we're back to the same problem that the circumbinary folks are worried about in the supermassive black hole binary context, right? Does the gas harden the thing or soften the thing? How far does that go? What happens? So we showed with some work, Amy Secunda led this, where we dropped in like 10 stellar mass black holes in an AGN disk. We just applied a migration torque prescription and let them meet each other. And we did calculate the actual gravitational forces between them. And she found that they would form bound systems quite quickly in short time scales. So you can see up here, this is sort of tens of thousands of years. They would meet and they would form a binary. And we just assume, let's just say that they merge, right? So if they do actually merge that quickly, then it's a fantastic gravitational wave source. But that's probably unrealistic because as I just mentioned, gas can probably harden some binaries and maybe soften some others. And so there's a lot of work on this, including just this morning, Adam Dempsey, hopefully he's going to talk about this tomorrow, some 3D simulations of binaries in AGN disks. There's a little bit more complications, I would say. And we can't directly apply the circumbinary models from the models where you have supermassive black hole binaries and a circumbinary disk to the same situation for a couple of reasons. One is that the disk is going to be a lot physically thicker, and so this thin disk, thick disk, right? Maybe that's actually bad news for these binaries. There's also a shear aspect from the disk, so you're not at the center of the disk. And it is not clear, for example, whether you'll be able to form mini disks, right? Because you would have to be able to cool, and the radiation has to be able to actually get out so that you can form a thin disk around individual objects or not. So this is all, very aggravatingly complex, but exciting and fun physics. But the thing is, if these things come together, they form a gravitational wave source, and that is a direct probe of the disk midplane for AGN disk modelers and AGN observers, right? They're sitting there, and they're subject to all of these gas physics, and they're also subject to dynamical interactions, which I'm going to talk about in a moment. And if we never see any, if we can be confident that there are no binary black hole mergers at the stellar mass scale happening in AGN disks, that also tells us a tremendous amount about what is going on in those disks, right? It would be a little bit pathological, actually. So if you can do these mergers at small scales and you can keep it going, you can actually create an intermediate mass black hole. And so I'm just showing this to show a mass distribution. And you can see that this was a Monte Carlo simulation, so we sort of abstracted away all the physics and assumed that we can write it down and know what we're doing. And we start out with this sort of black mass distribution, and after about a mega year, you end up with a several hundred solar mass black hole. This is kind of cool for a bunch of reasons. One, the mergers that make that thing are detectable by LIGO. Two, this thing is now sitting in an AGN disk orbiting around a supermassive black hole. So you have a LISA source with a free electromagnetic counterpart, right, by definition. Maybe it's not detectable, but if we think that it's there, maybe we can be clever and learn some cool things. If you are just throwing things together in the AGN disk, and the AGN disk is not very long-lived, you start out with some isotropic spin distribution, you can get some kind of chi-effective distribution, the effective spin of the binaries, and you would expect it to look pretty much like any other kind of dynamical interactions because you're just throwing them together randomly, and it's not really different from a globular cluster. However, things may be a bit more complicated depending on, for example, whether there is other dynamics, right? The fact that there is a disk establishes a preferred plane, which changes potentially the dynamical interactions. So there's a nice paper actually led by Johan Samsing and with some of the authors in the room, looking at how the sort of three-dimensional interactions versus two-dimensional interactions changes the expected dynamical outcomes. There's also, just to talk briefly about gravitational wave observations right now for folks who may not be particularly involved in the gravitational wave LIGO phone number conversations. There are two events with notably unequal mass ratios, and those are somewhat challenging to explain. Stellar modelers have some suggestions and ideas, but in an AGN context, because the migration rate depends on the mass of the migrator, a very common situation, not the universal most common situation, but a very common situation is that the more massive object is migrating from the exterior of the disk and comes up on several smaller mass objects, can easily form a binary with them. The binary merges, and so you get a relatively higher rate of unequal mass mergers from the AGN channel, and they're a moderately large fraction, not by any means dominant. But so it's quite interesting that in the first sort of 100 detections, less than 100 detections, there's these two unequal mass mergers. I'm not going to talk too much about feedback, but just as I've already said, feedback can change things in ways that are painful. This is not something that's been dug into super thoroughly, but there's some really interesting work here looking at, for example, how the opacity of the disk can impact whether feedback reverses the direction of migration or not. And, oh, good. Oh, I'm doing better than I thought. Okay. If you allow feedback from accretion onto a stellar mass black hole to change the direction of migration, we can apply an analytic prescription, and it depends on several things. It depends on the luminosity, right? So if the luminosity is going to depend on the mass of the accretor, again, and so it's not universally the case that, a 10 solar mass black hole often won't care about the fact that there's feedback. It won't change the migration direction, except for very optically thin regions. Whereas if you get to a larger mass, then it does tend to change the direction of migration. And so we have some Monte Carlo code work that we're trying to implement that in a sort of a simplistic way. And it doesn't change the number of mergers that you get overall, but it does change their mass distribution a bit in ways that are interesting. Okay. However, if you have a binary that forms and is not forced all the way to merger by the gas, which is probable that you won't get all the way there by gas, then you have the opportunity for dynamics to come into play. And so you can have, for example, asymmetries between prograde binaries and retrograde binaries, which may be preferentially ionized or broken up through dynamical interactions or sent all the way to merger by interactions. You can also have eccentricities that can become quite large because of dynamical interactions. And so these are kind of, these are very interesting and, of course, complicated additions that we have to worry about. So we're not just dealing with gas, we're also dealing with gas plus dynamics. I'm going to skip that for right now. The one thing that I want you to take home is that AGN are likely to be the home of the highest mass mergers, unless it is really hard to drive binaries to merger. And the reason why is because hierarchical mergers need to live in a deep potential well. So if you are two stellar mass black holes and you merge, yay, you've merged. If you would like that thing to merge with another thing, you need to do it in an environment where the stellar densities are extremely high. So you're talking globular cluster or nuclear star cluster. If you do that in a globular cluster, that first merger definitely imparts a spin to the remnant. Two spinning remnants hit each other. They're going to get a very large kick, and that kick is going to be larger than the escape velocity of the globular cluster. If you do that in a nuclear star cluster, of course, the escape velocity is huge. It's going nowhere. You get many, many bites at the apple, and so you can go very high up a hierarchical merger tree. And you might say, well, okay, so there's more nuclear star clusters that have no gas than there are AGN, and that's true. However, I would argue that because the rate of binary production is higher in AGN, and the lifetimes of binaries in AGN should be shorter than they are in bare nuclear star clusters, because the gas should, if we think that we understand the gas, if the gas accelerates the merger, then AGN can win and will win. So that's it. Yeah. Okay, I'm going to leave this up here and just point out that there's going to be some stuff in the discussion session tomorrow looking at independent EM constraints on what the AGN fraction actually is, which is, of course, exciting because then you can just reverse engineer things, even if the fraction is 0. Okay.
Thank you, Saavik. There's so much stuff in disks.
I didn't get to talk about the stars.
Okay, so we would like to start taking questions from students first. You have priority. If you do not yet have a PhD, you are #1 for questions. Ah, back there.
Hi, this is Magdalena Saavik. I had a question about accretion rates. So if you have a LIGO progenitor in an AGN disk, what kind of, do you think it would accrete at Eddington, like high Eddington ratios?
So we've modeled it a few different ways, and other folks have as well. I mean, so probably it's not going to accrete at Eddington. So if you have this very large flow, right, and you have this very fat disk, then you might accrete at Bondi. You might, it is not immediately obvious to me what the right accretion prescription is. We have analytically tried a few different ones, but the thing that I guess I would say is that binary formation happens pretty rapidly. And so if you think that they can form binaries pretty quickly, when you're paying attention to what's happening to the mergers, you may not have to worry so much about accretion if they're merging, or at least they're forming binaries in very short time scales, 100 meg, or no, sorry, not 100 meg years, 100,000 years or less, then maybe you don't have to worry so much about the accretion.
Hello, I'm Javier Roulette.
Yep.
You mentioned this possibility that in this the heavier black holes migrate faster and then can eat other black holes and then make an equal mass ratio merger.
Yeah.
In this case, would you expect that the heavy black hole would be spinning because of all the mergers?
So if that's the case, right, so yeah, you may expect that in those more unequal, if you have like a first generation merger, right, where you just have two random black holes and one happens to be heavier than the other, the first one comes up on the second one and there's no preference, right? But after that, then yeah, right, anything that's a higher generation is going to have a higher spin. And so off the top of my head, I don't recall what the unequal fractions might be in that case, like how many of them are first generation versus higher generation. The overwhelming majority are actually first generation, right? Like in any merger tree, the most common thing is like nothing super exciting. You have to get the highest generations are always the smaller fraction. So yeah, I would have to look actually at the stats. I don't know.
Yeah, so it's you here and then Julian.
Hi, Nicola Veronesi from London Observatory. So you mentioned that like unequal mass binaries are hard to explain through others formation pathways. Like, okay.
I don't want to. I mean, I know there's some of my best friends are stellar modelers. I know that it's possible to get unequal mass mergers out of standard isolated binary formation channels. It's just that there's a very high observed fraction of unequal mass mergers, right? And there's sort of a detection bias slightly against them. So it's sort of notable how high the fraction is in the first sort of order 100 detections.
So yeah, exactly. So my question was like, can we use somehow the mergers that we have actually detected with those Qs, so with those mass ratios? Can we exploit those detections to infer something about the fraction of the merger rate that come from AGN?
Yes. Yes. So, okay. So great question. The answer is yeah, right? So you can sort of take a handful of weirdos and hope that, but you have to know what your whole distribution looks like. And at the moment, I guess the issue is, if you think that we understand the physics reasonably well and that gas physics shrinks the binary to, let's say, half of its initial semi-major axis from like the Hill radius where it forms and gets it in halfway on short order, then I think a lot of our other conclusions are robust. And the answer is somewhere between sort of 20 to 80% of the LIGO mergers should be coming from AGN disks based on the handful of weirdos that are sort of overrepresented in the current sample, and how many total AGN mergers you'd need to produce that number with like large error bars depending on various measurements. And yeah, but it's sort of, it's an interesting fraction, which is why I'm really hoping that we'll get to talk about this paper. There's sort of an independent association strategy where if you just look at what essentially like what is the correlation function of LIGO error volumes on the sky to known AGN, if there's an excess, then you can attribute, even with the very large LIGO error volumes, you can estimate what fraction of all the LIGO detected mergers are coming from AGN or any rare source type. Actually, you could do it for other things. And so then you have this independent measure, which doesn't rely on this. And then you can sort of infer all kinds of things about your disk physics, because now you know that you have some fraction that are actually sitting at the midplane and giving you that physics.
Okay. So Julian, if you could keep it really quick while we're moving over to Chris.
I can speak fast.
Great.
I actually had a pair of questions. One of them is, how long does it take?
Just one, Julian.
Okay. Okay. Then I'll skip to
You know where to find me.
Yeah. Question. You spoke very frequently about the rapidity of binary formation. What exactly is your mechanism for forming a bounded pair?
So the individual objects are migrating, encounter each other in the disk. And if we, so basically in the simulations that I was showing, you write down the analytic migration torque prescription. And then when the two, and you put it into an n-body code, and when the two objects encounter each other and they're at less than a Hill sphere, you look at their relative velocities and their distances, and you calculate whether the energy is positive or negative. And much of the time, though not universally, it is negative. And so we say, okay, we have a bound system, that's a binary. So there is some of the excess velocity is taken away by the gas implicitly.
Okay, let's thank Saavik again for a great overview. Thank you.